Hello, this is Phil Thomas. I'm looking at a Paradise 70 watt KU band SSPA. Currently I've attached a dummy load to the output flange, and I'm going to use a frequency generator to generate between 14 and 14.5 gigahertz. So in other words, this is a KU band device. I'm just going to connect the power and we can start working with it. Okay, it's a little creaky. And here's some bad news. The fan on the left-hand side is obviously not working. So I'm going to have to take this apart, get the model number of the fan, and I'll probably order 2 new fans. So that's all I can do for the moment. I'll join this video again once I've got the fans and I begin to take it all apart. Okay, we've got a couple of extra fans. I'm going to have Dan do the installation because I have 4 thumbs on each hand and not really competent to do that. So I'm going to pass you over to Dan and he'll discuss what needs to be done whenever we replace fans on this type of unit.
Good morning, this is Dan with New Era Systems, and we wanted to do a quick review on the troubleshooting and fan replacement on this Paradise 80 watt KU band transmitter. First thing I do want to mention that is standard procedures, but some people aren't necessarily aware of it. Whenever you are using any type of transmitter, make absolutely sure you have a load on the output. Whether you have an input or not is irrelevant, you always must load the output. Back onto the fan, what we had, this is the old fan that was removed. When you turn the unit on, this fan would try to start. You can see that it does actually spin freely. However, when voltage is applied, the fan just basically gets stuck pretty solid. So, new fan was ordered. Very simple process, but although you do have a couple of connectors here that are used, to feed the voltage to them. So the fan comes with this connector here, and just a simple process of cutting off this connector, cutting this connector off of the old fan, and soldering that in. Of course, make sure you use heat shrink to isolate the positive, the negative. So that would be 2 pieces of heat shrink there, and then 1 final larger piece to cover the entire solder joint, which is basically what's here. So here's a closer view of the actual connectors themselves, and again the solder with the heat shrink over it. One thing I do want to point out is you always need to be sure that it's actually the fan that has failed and not the voltage delivery. In the case of this unit, because we have 2 identical fans, very simple, swap the 2 connectors, make sure the problem followed the fan and not the connector. That being said, again, everything is soldered in, and before I complete the assembly, what I will do is plug the unit in just to be sure that the fans are actually working. Okay, so we connect our power up. This unit runs on 110/240, so we're set up on 110. Now, this is not installed yet, so you want to be careful in plugging it in to make sure the fans work. Don't stick your fingers in it, don't get the power connectors caught in it. So I'm going to hold it just like this. This way everything is clear. I'm going to go ahead and plug it in. And these fans, some of these fans will take the finger off, so again, I want to reiterate, be careful. You can see both fans are functioning, mission accomplished. Okay, so very quickly on the reassembly of this, if I may step back for one moment, whenever you take a unit apart to replace a fan or any type of maintenance where you have access to the heat sink itself, the big, one of them heat sink that's down under here, you always want to blow it out. You may as well, take the opportunity to go ahead and clean the unit out. You can drop your temperature as much as 20 degrees Celsius in doing so, depending on how dirty it was or is or was, because it's not dirty anymore. We did already blow that out. So then it's just a little bit of finagling to get this guy to sit in right, although this went very smoothly. From here we have 4 bolts that hold this in, And then, of course, once the final assembly is done, we go ahead and recheck it, retest it, just to be sure that, you know, everything functions 100%. So here we are with our Paradise 70-watt unit on the bench. As mentioned, the fans have been replaced. The unit is operational. Our bench test setup here is that we have a dummy load hooked up with a cross-guide coupler. Our coupling factor on that is 36.5 dBm, which we have programmed that into the power meter so that what I read on the power meter is actually accurate. We're using an HP synthesized signal generator to provide the input. This is an SSPA, so for the purpose of this video, we are running this with 14.25 gigahertz input. Okay, so as far as a synthesized signal generator, what we're doing here is, you can't see it there, but we're showing a neg 4.67 output. Excuse me, but I have cable loss, I have an attenuator in line for protection of the generator itself. So what we're actually inputting at the end of this cable, or the input to the unit, is neg 15 dB out. So again, we have neg 15 at the input to the unit, like this cable from the signal generator. So what we're going to do is a 1 dB compression point, where we're going to increase 1 dB at a time, and we're going to look at our output. Not going to go into details of what 1 dB compression point means, but it's a test that we do on every SSPA we ever ship. So briefly, we will cover that. Okay, so here on, again, every unit we test, we do a full, full bench test on. We have a test data sheet that we log everything, and the test data sheet actually gets put on the website so clients can review the test data, and also, of course, the data sheet does ship with the unit. This test data was done a couple months ago. We're redoing the test because of the fact that we did have a fan failure that Mr. Thomas had caught. So we're going to recheck to make sure our power levels meet what they're supposed to meet. The fact is the unit would not overheat with one fan failed, because it does have two high CFM fans on it. But of course it will run warmer than it should have, so hence the retest. So if you want to see the test data, you'll be able to see this on the website as soon as Mr. Thomas posts that. But in the interim, what I want to do is just a quick 1 dB compression test, so you have an idea of what we do test-wise. Okay, so again, we're going to increase our power 1 dB at a time. You'll be able to see the output increase. We do have a spectrum analyzer hooked up also to the sample port of the unit. That once I'm done with the compression test, I always take a look at the output, make sure we're not noisy, make sure we don't have phase noise, etc. So, increasing power 1 dB at a time. We're starting with 40.56. I am going to go back and log all this data, but to keep this video short, I'll show you the test, then step back and log everything. So 1 dB up, 41.5, another dB, 42.6, 43.6, 44.7, 45.8, 46.8. Remember, we started at 0.6, so we're actually increasing by 1.2 dB at a time at this point. We're not compressed whatsoever. 47.5, compressed by 0.1 dB. 48.0, we are now compressed by 0.4 dB. We go up one more, we're at 48.1, we're now fully compressed, and I'm going to back the power off immediately because that's also close to saturation. Okay, so again, the compression being 48 dBm, 48.4 is technically 70 watts. However, it's important to note that we are measuring at the output of the unit, at the flange, which there is a difference. So this is a coupled factor through a cross-guide coupler, etc. So this unit does meet specification. Okay, so now I will be doing all the test data, so we have that information available to our clients. I want to thank you for your time and have a wonderful day.